Hello guys, so in this lesson we're gonna explore another interesting design, which is the binary adder subtractor. It is the same circuit that can do both, either adding or subtracting, okay? Based on what? Based on our choice here, M. So if the user wanted to add two numbers, binary numbers together, he's gonna use or set this M to 0. If the user want to subtract, he's gonna add or set this M to 1. This M is just a signal, it's digital signals, either high or low. Okay, so in circuit terms, if you wanted to add, he will connect this M to the ground of the circuit. If you want to subtract, he will connect this M to the VCC or VDD of the circuit, the high voltage, whatever it is, the battery. Good. So let's check here or highlight first the design. The design, as I mentioned in the lecture, is just an adder, binary adder with some modification. This modification is basically this XOR circuit in here. Okay, if M is 1, the output of the XOR will be just the complement of A. Okay, at the same time, the input carry for the first stage for adder will be 1 as well. So at that time, we are adding A to B bar to 1 or plus 1 again. So B bar plus 1 is the two's complement of B, so this will be a subtraction. Also, if M is 0, the output here will be just B. I mean, for example, here will be B3, B2, B1, B0, and the input carry will be 0 as well. So basically, this is an addition. That's, the trick. Okay, and this is basically the second design. There is another design that is your homework, basically. Okay, so let's do that. So in here, let's check. Yeah, here is basically the input and the outputs of the circuit. Now we have in the inputs we have the two binary numbers that we wanna add or subtract, A and B. We have also M. This is also another input in which the user can choose whether to add or subtract. The outputs is basically the sum, okay, which is just 4 bits like the two inputs, the two binary number inputs, and the carry C4 here. We can call it C. Okay, good. So let's check what we want. So basically here we want another signal to represent these four outputs of the XOR here. So I will call this signal BN, okay, and it's basically 4 bits as well. We want also another internal signal to carry these carries, okay, these 4 carries, C1, C2, C3, C4. Remember, C0 is input, which is basically M, okay. So I have named another signal called the rebel carry, because again, this carry is rebelling, it's propagating with propagation delay. This is basically the carry loop, the rebel carry adder, framework. Good. In the beginning, we're gonna find or determine these internal signals, these ones, which I call BN. Okay, so BN, for example, BN of 0 here is equal to B0 XOR M. Okay, so again, using the generate signal, whatever the number of bits you have here is 4, but if you have 10, 32, 64, whatever, just using this for loop with generate statement, you're gonna generate all the statements that you want. If you want a 64, if you don't use generate, you will have 64 lines. Bn of 0 equal to b of 0 XOR m. Bn of 1 equal to b of 1 XOR m. Until Bn of 63 equal to m XOR b of 60. So it will be very tedious and error prone again. Good. So the generate statement will do that for you. Don't worry about that. Then we're gonna instantiate these four others. Okay. So the first one looks like has no, I mean, it has two inputs, which is basically A0 and Bn of 0. And its carry input is just M. Okay. And its output, it's basically the first bit of the rebel carry, C1, which is rebel carry of 0, and S0 or S of 0. Okay. Then the rest, full others, the other 3 here, has a kind of repetitions because their inputs is bn of this is 1. So the input here is bn of 1, a of 1, the output is c of 1, and the rebel carry of 1, or 1 minus 1, which is 0. Okay, the second is the same, bn of 2, a of 2, s of 2, and this is called the c3, although it is the third bit in the rebel carry signal. So it will be 3 minus 1, which is still 2. So we can generate, there is a repetition, there is a pattern. So we can just use one line like this and replace all the indices with I. Then the generate statement with the for loop will generate 3 lines instead of writing them and modify, and you have errors and stuff. The generate statement will do that for you again. So for example, for any case here, let's take this case, for example. Here is I is equal to 2, so A of 2, Bn of 2. The output here is the input here is rebel, the input here is 1, rebel carry of 1, so I minus 1. And the output is still 2, because this is 0, 1, 2. This is the third bit, or rebel carry of 2. Okay, and the output is s of 2. Okay, guys. Finally, here we should also represent as a carry. Remember, we have a carry output. This carry out is basically the last bit in the rebel carry signal here. And rebel carry signal has, the last bit is rebel carry of 3. So here we assign this bit rebel carry of 3 to our overall, carry output. Okay, guys, very, very simple. It's basically the same as the carry subtract. So if we explore the first, if we go back here, this is the 4-bit binary subtractor. Actually, what I have it changed here is just very simple change, this one. So Bn in the rebel carry subtraction was not B of I, and there was no M, of course. It's really very simple changes. As we go forward, we always use what we have and build upon it. Either build, in typing, instead of typing everything from scratch, we just copy and paste and make some little modifications. Or, with a higher level of thinking, we use what we have as packages and instantiate them and reuse them. Okay. One may say we already have a 4-bit binary adder before. Can we make a package out of it? And yes. Another way to do that stuff here is to you have already the rebel carry adder, so you can create a package out of this rebel carry adder. Okay, and just one line here, one line. Okay, and in that one line you're gonna instantiate this, or include or use this rebel carry adder. Okay, and just to connect its inputs to A and B bar, or Bn of this signal Bn, and it's connect its output to your output of the circuit, either S or C. So basically you have many options all the time. Since you have something in your cache, in your bank, which are the previous design, then you can again build upon that. You have some interest based on that credit that you have. Okay, good. So let's now check the test bench. So again, let's go back to this is our design now, the binary adder subtractor. So let's go and check our test bench. Test bench again is very similar to the binary adder the 4-bit binary subtractor. I just made some modifications just to include our new signal or input, which is M, and also now we have addition and subtraction. Okay, so we can perform addition. So I make some test for the for the addition operation, and I make other tests for the subtraction operation. Let's check that. So that part here I explained before when in the video of the rebel carry subtractor. Okay, so just review it. It's really simple. I just add this new signal here because we have a new input M. So M underscore N will be connected to M here. And again, when you instantiate your design, you should take care of the order. Okay. Good. So let's start by the addition. In the addition, m is 0. So I first assigned 0 to m, which means addition. So here the input is 0. That means we're going to add. In the addition, to save time, so we want to add a to b. You know that 0, for example, x plus y is equal to y plus x. So I didn't do the repetition. I mean, I changed a from 0 to 15 in this for loop. So a here is 0 to 15. And b, I change b from I, which is a, I mean, from a to 15. So for example, when a is 0, I will test the design in adding 0 to 0, 0 to 1, 0 to 2, 0 to 3, until 0 plus 15. Good. Then, when I put a equal to 1, I don't need to check again 1 plus 0, because I did in the previous cycle or previous iteration 0 plus 1. So I start from 1. So I'm testing in the case of a equal to 1, 1 plus 1. So b here start from 1, not from 0. Then 1 plus 2, 1 plus 3, until 1 plus 15. Good. Now I will increment a to 2. Now b, I will not set b to 0 or 1, because I already tested 0 plus 2 when a was 0, and it tested also 1 plus 2 when a was 1. Okay, so I will start b from 2. So the test will be 2 plus 2, 2 plus 3, 2 plus 4, until 2 plus 15. So that's basically why I start j here, which is basically b, or be assigned to b, from I, the value of a, to 15. Okay. And again, this line I explained before in the previous video, which convert constant. I here is just constant, okay, or variable. It's not a signal. It's not a real thing in your circuit. It's just for simulation. So to assign, so I want to say I equal to an equal to I can't do that directly like normal programming languages. Okay, it's a little bit complicated, because a here is something real, or represent something real, some wire in your circuit. So we do that, that line here, and which is just conversion stuff. And to do that conversion, we need to include this library, IEEE numeric standard, which convert standard logic vector to, which convert constant to standard logic vector. So here we'll convert I into some standard logic, value, and assign this value to A. And again for B the same. Good. This is for the addition. Now the subtraction. For subtraction, I should assign m to 1. So m now is 1. So the input carry here is 1. And of course, when you XOR something with 1, it will give you the invert of that thing. So x XOR 1 will give you x bar all the time. Good. So now for subtraction, we need also to do some other test. So something I messed up with you guys in the previous video, when we tested the binary subtractor, is that I also changed. I just used exactly the same loop that we explored before, but with one tiny difference. In the previous video, I was changing I from 0 to 15, and this is not quite right. Okay, it should be from 0 to 7, and the reason is that, remember, a here, I want to say a minus b, okay, in the subtraction stuff. Remember here, since we are doing subtraction, then we are dealing implicitly with signed number, not like the addition here. The addition is, I am assuming all the time, it's unsigned number. So when I say unsigned number, that means the most significant bit, is counted in the number. Okay, for example, 1 0 0 0, 1 and 3 zeros is 8, because the first 0 is 0 times t to the power of 0 plus 0 2 to the power of 1 plus 0 to the power of 2, then plus 1 times 2 to the power of 3 will give you 8. That's good. But in signed number, The most significant bit represent the sign of the number. So if the most significant bit is 0, that means this is a positive number. And if the most significant bit is 1, that means it's a negative number. So 1, 0, 0, 0, like this example here, is not 8, like sign number, no. So this is, since we have here 1 at the most significant bit, then this is a negative number. Okay, what is this number now? How to know it? If you guys go to our chapter 1, we discussed how to do that. We basically get the 2's complement of that number, and what we have from the 2's complement will be this number, and then we put some negative before it. So for example, for this one, 0, 0, 0, okay, this is not 8 again. So to get its number, this number, we do the 2's complement of that number. So it will be, we take the complement, it will be 0, 3 ones. Then we add 1 to it. So it will be 1, 0, 0 again, 1, 0, 0, 0 again. That's good. But now this is 8, and since this is not the original form was this, so, and this is a negative, so this is negative 8. So 1, 0, 0, 0 is negative 8, not 8. Okay? And you can have many, examples like this. Okay? That's good. That's good. Okay. So basically 4 bits, if you also review our chapter 1, if you have 4-bit binary signed number, these 4 bits represent the range of numbers between 7, positive 7, to minus 8. To minus 8. Okay? So going back to our design. I am saying all the time A, so I'm assuming always A, it's a positive number. And B, would be less than A. So I can, when I say A minus B, I will get a positive number. Okay, just to make the test easy for us. But of course, B can be bigger than A, that's fine. But it will give you some negative number that, and then you should, it will be harder for the test. I mean, for our eyes to catch if the operation is correct or not correct. So I just choose to make B less than A. So first A, we know, as I said now, A is positive number. So that's why I make it from 0 to 7. And remember again, I said that 4-bit binary signed number represent range of values from maximum positive 7. That's why the range here stops at 7. Okay, not 15. Because 4-bit, if it's signed, if it's unsigned number, it can 4 bits. If they are 4 ones, this is 15. That's basically the difference. Okay, between that test here, and it was exactly the same in the subtraction, but I did A15 here, which is not correct, because 4 ones is not 15. It is something else. So we should get, it's -1 basically, because we should get the 2's complement of these 4 ones. Since we have 1 at the most significant bit, this is a negative number, so it's not 15. So to get its 2's complement, we complement it, so it will give us 4 zeros. Then we add 1, so it will be 1, 0, 0, 0. Okay, 1 in the least significant bit, and then 3 zeros in the higher bits. So this is basically -1. Okay, good. So that's basically the subtraction. Okay. Nothing else has changed. So let's now simulate this. Start simulation. Work, and then choose a rebel carry adder subtractor. Start by R, so it will be down here. Rebel carry adder subtractor. Yeah, that guy. Okay. That's fine. It's not a big modification. So it complains because I changed, but it's not a big change. I mean, I just add some spaces or something. I didn't change. So we can just use the original version. Okay. I didn't put some new code. I just put some spaces and stuff. It doesn't affect the code. Good. So these are the inputs and the outputs. You put them here. Remember what differentiates subtraction from addition is M. So I'll get M here after the two inputs, A, B, this is M. Then S is the sum and the carry. And I will mark M with a different color, like yellow, for example. Usually use yellow because if you use red, red here is used specifically or to represent undefined signal, which is something which means you have some mistake in your design. So use yellow, not red. And also let's make all these guys as unsigned numbers. Radix unsigned. And we have maybe 200 or less than 200 cases. So I'm gonna, make this as 100 and run twice. So we need also to zoom out a little bit. Where is the zoom? Here is the zoom. Good. Now let's check what we have. So M now, look at the yellow signal, M. M is 0, look, M is 0. Because we did here is, if you go to back to the test bench, the addition is before the subtraction. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 15 until, 0 plus 15 is 15. And now look, starting from 1 plus 1, because we don't need to do 1 plus 0 because we already did that when A was 0. So 0 plus 1 is 1. So here 1 plus 1 is 2. Until 1 plus 15 is 16. 16 is 5 bits. So the carry bit here, has a meaning. I mean, it's part of the number. So if you look here, 5 bits, the most significant bit is 1, then 4 zeros. So this is 2 to the power of 4, which is 16. Let's continue. Again, A here is 2, and we start to be from 2. So 2 plus 2 is 4, 2 plus 3 is 5, and 2 plus 4 is 6, and so on, until 2 plus 13 is 15, 4 ones, and the carry is 0. But now, 2 plus 14 is 16. So that's basically 16 again. So 5 bits. The carry bit here is the most significant bit. 2 to the power of 4 is 16, then 4 zeros. Then 2 plus 15 is 17, which is 16 plus 1. So we need here another bit in the least significant bit is 1. So 5 bits. The carry, which is the most significant bit, is 1. And in the sum, you have 1 at the least significant bit and 3 zeros in between. Okay, that will give you 17, and so on. You can continue like that. Let's check some other, in the higher values of A. Yeah. So here, for example, 12 plus 12, which is 24. 24 is 16 plus 8. So the sum is 8 and the carry is 1. Carry 1 means 16. And sum is 8. Then you add these together. This will give you 24. 20 plus 13 is 12 plus 13 is 25, which is 16 plus 9. And so on. 13 plus 13 is 26, which is 16 plus 10. So you have here 10 as the sum, and the carry is 16. 15 plus, look, 14 plus 14 is again 28. 28 is 16 plus 12. Okay. Then 14 plus 15 is 29. 16 plus 13. Then you have finally 15 plus 15, which is 30, which is 16 plus 14. Good. Now we finished all the cases of the addition. Now we go to the subtraction. So in the subtraction now, 0 minus 0, 0, and that's it. Because in a subtraction, look guys, we start from I 0 to 7, and then J from 0 to I. When I is 0, the J here will be from 0 to 0. Okay, so 0 minus 0 is just one case. It is the opposite of the sum, of the addition. In the addition, 15 is is the case that you just have one case in it, 15 plus, and that's it. Okay, here is 0 is like the 15, it's just one case. Then A become 1. So J will iterate from 0 to 1. So we'll have 1 minus 0 and 1 minus 1. Good. 2 minus 0, 2 minus 1, 2 minus 2. Those 2 minus 0 is 2, 2 minus 1 is 1, 2 minus 2 is 0. Then 3 minus 0 is 3, 3 minus 1 is 2, 3 minus 2 is 1, 3 minus 3 is 0, and so on. Let's check for, yes, this is the maximum case, 7. 7 minus 0 is 7, 7 minus 1 is 6, 7 minus 2 is 5, 7 minus 3 is 4, 7 minus 4 is 3, 2, 1, 0. Okay? Thank you, guys. That's it for the, for the binary adder subtraction. Thank you for watching this video and see you in the next video. Bye-bye.